Yes, hi, this is Clifford Carnicom, and I'm here with Mark Kilcoyne today, and we're going to be having a discussion primarily on Mark's side about some of the recent research that has been done. This research is on the very forward edge of what I've been able to do, at least on the Morgellons issue. And Mark Kilcoyne has an extensive background. Both he has an active interest in the research as well as an extensive background in biochemistry and nutrition, and he's here today to give his thoughts and comments. He's aware of some of the research that's been done, and so I'm going to give the floor mostly to him. Mark, thanks a whole lot for being here today. I really appreciate it.
Thank you, Clifford.
And Mark, if you wanted, would you take just a second? I know you were at our conference last year in October of 2011, and the audience was very engaged with your talk very quickly. I know that. Could you give just a short background as how did you get involved in the type of field of study you are? I know you have a lot of knowledge on the nutrition side, and we share a common interest in biochemistry.
Bachelor's in nutrition, 3 years of college chemistry, and I've been studying the effects of toxic mold since about 2002. So just because of my own sensitivities to it and my interest, basically, because it's been almost avoided by the AMA, the medical health community.
Super. Yeah, I know that you're pretty much a walking legend where you work with people seeking information, myself included. So anyway, thanks a whole lot for being here. And you and I have had a little bit of time to go over some of the research that I've been involved in over the last 2 to 3 years. And you know that I've had a particular interest in getting specific knowledge about the nature and structure of a particular growth form associated with what we call Morgellons, and I do a lot of work with culturing, and you're aware of some of that work. But I've been after seeking specific sort of structural and biochemical knowledge about this growth form over the past couple years. And I'll talk about my papers in more detail at another time, but you and I have had enough of a discussion where you're aware, at least, of the general basis of that work, and also the general chronology of that work over the past couple years. The first couple years ago being more general and basically a process of learning about disease in general and how we start to thwart disease in our body through the roles of antioxidation and enzymes and this type of thing. But that knowledge was actually a bit on the more general side, with the exception of very specific knowledge related to iron. Work on the existence of iron within this structure did come out in that earlier work. More recently, over the last few months, I have done work related to identification of specific amino acids, cysteine and histidine, that we're going to talk about today. And then also some what you call mitigation or counter strategies involving reduction techniques of trying to break the bonds of this structural form, which appears at this point to involve the two amino acids, cysteine and histidine, an iron core, sort of a chelated iron core, and primarily in an oxidated state, a +3 state, it appears. And then reduction techniques currently being involved with the use of vitamin C and N-acetylcysteine, NAC, and then also glutathione coming out as an extremely strong role here. This is what my work has done. I really will turn most of the floor over to you, but I wanted the audience to have that general background, and I'll follow my papers up later. But I wanted you to have some time to comment from sort of a comprehensive view as to what you see in this body of research and your knowledge of nutrition, and what do you see emerging from this research, and what do you think is relevant for us to be studying?
Well, I think all of the above points are relevant, and iron being one of the main ones, because of course we need iron as a basis for hemoglobin, the protein that carries oxygen around in our bodies, which makes life possible for us. And pretty much all species, at least vertebrate species on the planet. And so I think that's a key point. And also the I guess the Morgellons, you'd like to call it, right?
Well, this is the name that's been given in in sort of a cultural form.
I mean, if it utilizes those two amino acids, cysteine and histidine, of course, it's getting it from us. So, which processes of health is it disrupting by doing that? And of course, cysteine is a precursor to glutathione, as you mentioned before, and glutathione is also used by the body in breaking these sulfur bonds down in pathogens that we encounter, that get into our system.
Right.
So it's both weakening us by stealing the components for glutathione, and also it's weakening us through sequestering or stealing the iron out of our hemoglobin and oxidizing it to the Fe3 plus state. And the histidine, too. Histidine is one of the two components, including alanine, of L-carnosine. Carnosine is a very important dipeptide.
Yeah, talk about it. That's the first time I heard of carnosine, actually, the other day. So
very important peptide for anti-aging, for stem cell production, which is incredibly important for us repairing our existing protein structures in our body.
How does it relate to either cysteine or histidine, if those are acknowledged to exist in this, through further work? How does carnosine relate to the existence, say, or identification of cysteine and histidine?
Well, carnosine is just the one of the end products of histidine, a very important end product that tends to decrease with aging. So the more that you disrupt that carnosine synthesis, the more you're breaking down the body's repair processes and increasing the effects of aging, making it much more rapid.
See, one of the questions that comes up there, and I want to back up actually to the iron, but one of the questions that comes up there to me is that if you identify that these amino acids are there and that they logically are stealing that or robbing that from our body, a very logical and intuitive approach might be to just simply take those amino acids in a direct form as a replacement. And I guess the question is whether or not that's the most effective way to go.
Not the most effective.
And
the
that's
cheapest way for
about.
sure. Histidine is much less expensive than L-carnosine, but it's a very expensive enzymatic process for the body to put alanine and histidine
meaning
together.
That it's taking additional energy.
That's right.
That's the payoff for that.
And that's right. So you're bypassing that step, and you're going straight to the carnosine and directly increasing your stem cell production. And it also has many other anti-aging effects by decreasing glycation in the protein tissue and the formation of AGEs, or advanced glycation end products, which are basically the cross-linking of glucose and any kind of connective tissue protein, usually collagen, in the tendons, ligaments, or muscles. So it directly inhibits the body's repair of its protein structures, which hold us together, literally.
So this would be tied in with the joint. As I was looking at the effects of cysteine and histidine deficiency, the cysteine is coming out very, very strong on the oxidative stress aspect, and then the histidine was coming out very, very strong on the joint. And this is what you're starting to talk about,
the
right?
The cysteine is also directly involved in collagen production. One of the most
collagen? What's collagen?
Collagen is the body's basic connective tissue protein. It's responsible for about 30% of our body weight in healthy individuals. Collagen's 50% of the bones. It provides the bone's flexibility. It's the non-mineral portion. It's the scaffolding by which the body transmits calcium and other minerals for the formation of bone salt or bone material. Anytime we break or stress a bone, and there's just normal turnover of bone, it takes about 7 years, but the bones are replaced on a very regular basis. It's just a slow process. But once you weaken that collagen scaffolding that the bones are grown around and it keeps them flexible, you're basically deteriorating
brittle.
the bones.
It
yeah, it makes them
brittle.
That's exactly right, which is, of course, part of the aging process as well. So you're getting the acceleration of many different aspects of the aging process through this one organism.
You're saying that both cysteine and histidine are very directly involved in the formation of collagen, is what you're saying? Is that right?
The formation and repair.
And then
the histidine comes more in the repair process through carnosine, And the cysteine itself is directly linked in the sulfur bonding process in the collagen structure.
And you're also saying, though, that a more sort of direct route towards the formation of that collagen, in contrast to taking histidine directly, would be the consideration of taking carnosine.
That's
Is that right?
That's right.
And that's because there would be an energy expenditure.
That's right.
In trying to.
And it's a very expensive
use histidine.
process, and the body tends to forsake that process as enzyme production drops. And enzyme production drops fairly early in life. We're born with, they say, a certain enzyme potential, and the more cooked food we ate and the more exercise we do, etc., the more we use up those enzymes for digestion and systemic anti-inflammatory purposes.
This is collagen on the screen there. I guess I don't know if is that the form of it. Do you think there that's showing on the right?
That looks like it.
It must be the form of it too. Then, and they're saying exactly what
and
you were saying.
And there's many sulfur cross links in there. Sulfur bonds, sulfur dioxide bonds. Actually,
this is exactly what you were saying in terms of connective.
Yep,
right, main component of connective tissue.
25 to 35%, usually about 30, but yeah,
right.
More in athletes.
I want to actually back up on this iron issue first, and then we'll probably come back through this chain.
Oh, I forgot to mention collagen's
yeah, sure.
also one of the major components in our intestinal tract too.
Now you were saying, as I understand it, our bodies are roughly 50% protein in general. Is that right? Fair enough?
When you take away the water, yeah.
Roughly.
Well, the bones are 50%.
But you were saying that the collagen alone is you said how much of the bone?
50.
Yeah,
in young individuals.
Half of the bone itself, you're saying, is
right.
collagen.
In young, healthy individuals.
And then half of our body roughly is protein.
And
so that's roughly a quarter.
And you can see from infant to adult, the baby's bones or infant's bones are completely
very
flexible. Extremely.
This is why a baby can fall on the floor and hit
not
their head.
break anything.
Exactly.
Adults, totally different case.
Exactly.
So really brittle bones, the collagen structure is already breaking down. It's the flexibility's gone. That's primarily due to collagen loss.
So, as I'm hearing this, and it's great to get your feedback on this, that, I can do work on identification of these particular amino acids, but you're sort of putting the role of these amino acids in place, and you're saying that this is a very dominant role of both of these.
Extremely dominant.
Would be our bone structure and collagen, and the joint pain has come out as being a dominant
joints,
symptom.
Bones, intestinal tract, cardiovascular system. It's almost all of our connective tissue with a few exceptions.
Now, boy, there's so many things I want to cover here, but on the cysteine, in the work that I've done thus far, there's pretty strong work indicating tie-ins with oxidative stress, which is coming out to be a real strong indicator here so far in terms of what I'm seeing. Tell me if you know what the connections, if any, would be from your side. I'm finding the papers on it, so I know it exists, and I'll try to bring up one or two here as we go along. But what do you know, if anything, about any connections between oxidative stress, the free radical issue in our system, and any deficiencies in cysteine? That's one that I have a strong interest in. This is one of the papers that I found from NIH, I believe. Yeah, I think NIH was on this one. But this is exactly about this, where they're saying there is cysteine are tying in directly. Oxidative stress are tying in with cysteine deficiencies, and I'd wonder if you'd ever heard of that kind of role going on, because that's what I'm running into, and I know that oxidative stress appears to be a primary symptom that's coming out.
Absolutely. Biological sulfur or cysteine is one of the building blocks of collagen. And there are other important building blocks like proline as well. But the cysteine part of the collagen structure tends to be more greatly affected by oxidative stress than other parts of the protein.
Yeah, it's interesting.
So it's replaced on a more regular basis.
I see. So that that's another issue to this. It's really come out very strong as the oxidative stress, and I just wanted to point that out for people at least to be looking at these two issues, right? If we're looking at issues with oxidative stress, to consider the role of cysteine with that, and then in joint pain, to consider histidine. And in what you're saying, the crossover between both of them.
And then the other crossover for cysteine, of course, is the production of glutathione.
Okay, and
that's an antioxidant, so it's working directly against.
This is a big one. We're going to be talking about this real soon. I'm going to get to. I want to back up on this iron thing. We have a question from Carol. Say it loud, and I'll try to repeat it.
Can you give a definition of oxidative stress for people who may not be clear about what that definition is?
Sure. Carol is asking, what do we mean by oxidative stress? I'll give mine in a very layman term, and then you can give yours. But oxidation technically it's the loss of electrons. That's technically what it is.
Exactly.
And then another way that I see that in terms of my readings is electrons essentially mean energy. And so if we say that we're losing electrons, there's pretty much a direct relation between that and the loss of energy, because your electrons are one of the primary sources of energy that there are. So this would be one interpretation. A more lay interpretation of oxidation is essentially rust, in terms of relating to things that we know. When you see metal rust away, that's a process of oxidation. Oxidation can take place in your body just as well as it can take place on a piece of metal or iron, and it wears the body away, is what happens. That's my general lay interpretation as well as a formal definition.
That's about right.
Do you have anything that would be different or add upon that?
You hit it right on the head. It's stealing of electrons by free radicals, basically, or reactive oxygen species, as they call them.
Right. And this whole electron transfer thing is very critical. It is the flow of energy. Electron transfer is a flow of energy in the body. It's the
directly involved with production of ATP.
Exactly. ADP
Our
and
cellular
ATP,
energy source.
Production of energy. Anytime at all that you have an imbalance or some kind of skew in the flow of that energy or electrons, you're affecting the ability of the body in an energetic sense. Right? Fair enough?
Yeah, sure.
Okay. I want to back up to this iron thing a little bit and go back to the core of that, because the finding is actually pretty profound, but it's beyond sort of debate at this point, but a core structural component of this growth form being Morgellons filament samples as well as the cultures that have come from them. A core component of that is iron. And this iron is in a more oxidated state, which is tying in with what we were just talking about. Now, iron in the blood needs to be in a particular chemical state in order for our bodies to use it and to get oxygen. The binding between iron and oxygen in our blood only takes place if the iron is in a particular chemical state, particular oxidative state. If you change that oxidative state of that iron, it will not bind to oxygen properly anymore. So that whole bonding process with oxygen is disrupted. And oxygen is ultimately the source also of all energy in our bodies. And the process of respiration is the process of energy creation. I'm going to have my comments, and I'd like to have you add on to them afterwards in terms of what we see. But when this iron has been affected, it basically has been pulled away from the hemoglobin. It would seem to me that we know it's in there, so it had to be pulled. We know that we're talking about stealing.
Yeah.
We know we're talking about stealing already in the amino acids, and now I'm backing up to the iron. And the damage that is done by the removal of this oxygen, to me, it just seems like it has to be immense, because it's at the whole core of our whole respiration process, right? And the work is showing that this growth structure is a combination of this iron and sulfur and amino acids right now in a dipeptide form.
Histidine and cysteine.
I wanted you to sort of elaborate on your understanding of the role of iron in the body. And then also the question, if it's not necessarily okay just to have iron, first of all, it has to be in the right chemical state, the right oxidative state. Yeah. Okay. And then secondly, what's the impact of that being stolen or sequestered from your body? I'd be interested in your thoughts on this too.
Okay. Well, you've got not just cellular respiration, which is directly dependent on iron, but also the overall alkalinity of the body, which is directly correlatable to the oxygen content, VO2 max, of the bloodstream. So, the more alkaline the body is, of course, the less pathogens are going to proliferate in that environment.
Exactly.
Anaerobic bacteria and
Right.
viruses generally like an anaerobic or low oxygen environment. So that's another part of the acceleration of the aging process through, basically acidifying the body by stealing the iron and thereby the oxygen away from it.
Right, you're just calling to mind some reading I was doing on this
then-
glycolysis and cancer.
And not
Relationship.
cancer also thrives in an anaerobic environment.
Exactly.
But not only that, our immune system needs free oxygen to function because it creates superoxide anions to destroy pathogens. So it's directly causing a malfunction of our immune system by robbing us of oxygen as well, which is a further delineation of stealing the iron.
Right. What's going to be very interesting to me too over time is to pull the information that we're seeing from the research side and develop a composite picture from this information as how it's likely to affect the body, and to establish whether or not that's correlating, with what we're actually seeing. And basically what we're seeing, what appears to be happening, is we have a major breakdown in the immune system taking place.
And not only that, we've got at the cellular level much higher oxidative stress, possibly due to the loss of oxygen and corresponding damage through free radical damage inside the cellular mitochondria, which could be responsible for all the chronic fatigue.
Right, again,
disease
interfering with the energy production and energy flow, right?
Yeah.
Yeah, exactly right. Exactly right. So this gets us through some of the information on the iron and some of the information on the amino acids. And then over time, in the future, I hope we'll talk more, but we're starting to construct this picture, this scenario of how this is affecting this, and then likely affecting us. And everyone understands, I say it every time on one of my papers, I'm not acting in a medical capacity here at all. I'm acting as an independent researcher. There's no medical advice being given here. It's informational. And that qualifier is just about on everything I've written there. But we are trying to make this information available to the public so we can start to look ahead. Part of why I wanted Mark involved here is so that we can start looking ahead and extrapolating where this information is going to, beyond the limits of what I'm able to accomplish in my particular sphere. The next topic that we can devote at least just a couple minutes to, because I know you don't have a whole lot of time here, and we'll come back again, but this topic of now reduction, I have a specific goal of trying to learn how to interfere with the basically the protein synthesis, the formation of this protein, which is a dipeptide form, is what it appears. A specific objective of learning what that molecular structure is, and then trying to go to work on interfering with that molecular structure, and or learning how to break down the bonds of that structure, as well as make that iron accessible to the body. This is what I've been working on. And we won't have time to complete it today, but the recent research indicates the possibility, likelihood of 3 reduction techniques that are expected to have some effectiveness here. All of my work is in the laboratory. It's not in the body at this point, so there has to be an extrapolation that takes place here by necessity. But the work is indicating that vitamin C, one of the antioxidants, as well
and
as
also
in...
collagen booster.
Say again?
Vitamin C is also a collagen booster.
Okay, and actually, there's actually iron. There's lots of connection with vitamin C from what I can. There's a lot going on with vitamin C, but the use of vitamin C as an antioxidant appears to be having a effect, fairly weak at this point, but nevertheless there, in the particular pursuit of breaking down these bonds, which appears to be a very difficult issue because the core of them appears to be a disulfide bond. And if we look into disulfide bonds, this would be a great thing to bring up here if I can. This is one of the strongest bonds there is in the world of
very difficult
chemistry.
to break.
And the easiest example of that is your hair. your hair is formed in large part from disulfide bonds. And ask yourself, how easy is it for you to break down your hair? It's one of the most,
It goes
it's going
through
to clog
the
up your
digestive
sinks. And
tract completely undigested.
this is what disulfides bonds are about. So to find anything that can break those down without harming the body is a real challenge, and that's what I've been up against lately for the past year or so. But the candidates that are showing up right now would be briefly vitamin C. It looks like it may have some effect, and N-acetylcysteine, abbreviated as NAC. By the way, they have a form of NAC for carnosine too, because it's the same thing, N-acetylcarnosine. So they call it NAC also. But so the NAC we're speaking of here would be N-acetylcysteine, which is a modified form of cysteine. Right? I have to look up what the acetyl group is. It's a carbon hydrogen group of some kind. I have to look at,
right. That's right.
But we'll have to look at. But it's a modification.
Hydrocarbon. Yeah.
Modification of cysteine, and so that is showing effect. And the third one, being the most important one, that is just really at the top of my list in terms of where the research is going in the immediate future, but this is glutathione. The application of glutathione to this growth form is showing direct evidence of being able to very effectively break down those bonds, as well as reduce the iron from that +3 to +2 state. And I wanted you to have at least just a couple minutes today. I really do hope we carry on in the future, but have a couple minutes to comment on whether or not this makes sense to you in terms
Absolutely
of what's happening
sure.
and what it might mean for us in the future.
Well, I would actually clump N-acetylcysteine and glutathione together, because N-acetylcysteine is, of course, the precursor to glutathione. It's converted to glutathione.
But that, of course, I have to say, that, of course, the audience may not necessarily appreciate that, of course, because it's been a learning curve for me. When you raise the question of, glutathione, maybe if I have a problem, I just take more and it takes care of it. But we learned
Glutathione's not stable in stomach acid.
Yes.
It's more expensive. It breaks down in a low pH environment of the stomach. N-acetylcysteine's much more resistant, and it converts very effectively in the liver to glutathione without pre-existing liver conditions, of course.
So, one thing we learned from this, if you have something you identify, it doesn't mean you just take it. This has come up with all of these things. If you find something that's a part of something, it doesn't mean that you just necessarily take it and it takes care of the problem. We have to learn the biochemistry behind it and the connections or associations with it and other things in the body, right? And this glutathione is a classic example of this, in the sense that if you start learning about glutathione, you find the real story is in the precursors that you're talking about. The way that we form glutathione, we need what they call the precursors that lead to the formation. This is what you're starting to talk about, right? That NAC, to us right now, it might be, and of course, of NAC being the precursor, but it certainly wasn't when I started this research. And I learned along the way that you just don't absorb glutathione very easily.
That's right.
So we have to work on elevating, or if we're going to take that strategy, we have to work on elevating those glutathione levels. And what you're saying is that NAC is one of the precursors or tools that makes that happen. Do you know how that happens, actually? Do you know what the process is? Don't worry about it. Don't worry. No, you can get. I've studied them myself. You get into pretty heavy, chemistry basically, and molecular reactions taking place. But that's what is known, is that NAC is apparently a preliminary, earlier stage to the formation of glutathione. Is that right?
Yeah. Sure.
That's right. So that's extremely important, and this is why you were sort of combining these together. Is what you were saying.
Of course.
And
we might even discuss another form, acetyl glutathione, which is even
Please, yeah, you
stronger.
had mentioned. I'm really interested in this.
And you might do a little research on the internet. It's not often discussed in the health fields, but acetyl glutathione is a much more potent iron reducer, and in general, free radical scavenger, and heavy metal chelator, pulls heavy metals out of the body better than glutathione itself.
And you were saying, this is a problem, is what it amounts to. Let's say we're choosing, we consider the use of N-acetylcysteine as one of the precursors. Also, I'm learning that whey is apparently an important precursor to glutathione production, from what I was reading. Which is interesting, because there was an earlier tie in my work of lactoferrin in terms of helping to chelate the iron, to keep that iron
lactoferrin is an iron reducer.
Exactly.
Yeah.
So it has shown up twice now in research at 2 different stages.
And that's, of course, derived usually from colostrum.
Yes, yes. So that's a real, these precursors are really interesting to me, but what you're saying from what I hear is if we acknowledge that glutathione is not taken directly into our system, there are things that we might be able to do, take a modified form of glutathione, just like we're talking about taking a modified form of cysteine, N-acetyl.
N-acetylcysteine, sure.
That there's a modified form of glutathione that might be more helpful and beneficial in terms of assimilation into the body.
And activity.
Okay.
Activity.
And we keep referring to this term acetyl, and what we know is we have a chemically modified addition, acetyl group that's attached, that apparently is affecting the ability of these molecules and compounds to be assimilated into our body. Is that right?
Yeah, and acetylation happens in the liver, just not at a very high rate. So much easier to do it outside the body, acetylate the precursor, N-acetylcysteine, and then let the liver do its easy conversion into acetylglutathione.
Let's talk about that process a little bit, because with N-acetylcysteine and NAC, there are commercially available forms of that. That's something that's commercially available form.
Sure.
But the glutathione, what we're seeing is that may not be so readily available, and that means we will have to actually understand what that really means and what the process is. And you have made a reference to the use of acetic acid, which is in vinegar,
that's right.
Commonly in vinegar, to basically creating our own reaction there to make that form. And what you're talking about, apparently, there's a combination of glutathione in a form we can basically purchase or access, but combining that with essentially vinegar or acetic acid and forming our own modified form. This is what you're suggesting there might be an avenue. Is that right?
More potent, yes.
Yeah.
And not much more expensive.
Right. So anyway, that's great, Mark. I know you're running out of time, but I really want to thank you for being here today.
You're welcome.
I'm very interested in pushing out this knowledge base beyond just what I'm able to accomplish. I can establish certain steps here through painful processes that get us some base of information, but our source of feedback unfortunately has been limited thus far, and I really appreciate you being involved in this, and I'm looking forward to the future that we can keep taking this information, which is at the front edge of it, and see where it's going. In addition, we have some more rudimentary and basic work going on with a research project where we're trying to collect just fundamental physiological data to try and basically run a control study. So there's 2 levels of research going on. But this is a very exciting area in terms of becoming relevant now, rather than just becoming a laboratory exercise. We're getting enough information, I think, where we can actually start piecing together what the likely impact on the body is and what steps that we might be able to take to sort of counteract it.
Absolutely.
And you're a part of that process, and I really appreciate it, and I'll look forward to the next round if you'd like to continue.
Great. It was great being here.
Yeah, thanks, Mark.
Which makes life possible for us. And pretty much all species, at least vertebrate species on the planet. And so I think that's a key point. And also the, I guess the Morgellons, you'd like to call it, right?
Well, this is the name that's been given in, in sort of a cultural form.
If it utilizes those 2 amino acids, cysteine and histidine, of course it's getting it from us. So which processes of health is it disrupting by doing that? And of course cysteine is a precursor to glutathione, as you mentioned before. And glutathione is also used by the body in breaking these sulfur bonds down in pathogens that we encounter, that get into our system.
Right.
So it's both weakening us by stealing the components for glutathione, and also it's weakening us through sequestering or stealing the iron out of our hemoglobin and oxidizing it to the Fe3 plus state. And
of this structural form, which appears at this point to involve the 2 amino acids, cysteine and histidine, an iron core, sort of a chelated iron core, and primarily in an oxidated state, a +3 state, it appears. And then reduction techniques currently being involved with the use of vitamin C and N-acetylcysteine, NAC, and then also glutathione coming out as an extremely strong role here. This is what my work has done. I really will turn most of the floor over to you, but I wanted the audience to have that general background, and I'll follow my papers up later. But I wanted you to have some time to comment from sort of a comprehensive view as to what you see in this body of research and your knowledge of nutrition, and what do you see emerging from this research, and what do you think is relevant for us to be studying?
Well, I think all of the above points are relevant, and iron being one of the main ones, because of course we need iron as a basis for hemoglobin, the protein that carries oxygen around in our bodies.
How did you get involved in the type of field of study you are? I know you have a lot of knowledge on the nutrition side, and we share a common interest in biochemistry.
Bachelor's in nutrition, 3 years of college chemistry, and I've been studying the effects of toxic mold since about 2002. So just because of my own sensitivities to it and my interest, basically, because it's been almost avoided by the AMA, the medical health community.
Super. Yeah, I know that you're pretty much a walking legend where you work with people seeking information, myself included. So anyway, thanks a whole lot for being here. And you and I have had a little bit of time to go over some of the research that I've been involved in over the last 2 to 3 years. And you know that I've had a particular interest in getting specific knowledge about the nature and structure of a particular growth form associated with what we call Morgellons, and I do a lot of work with culturing, and you're aware of some of that work. But I've been after seeking specific sort of structural and biochemical knowledge. Yes, hi, this is Clifford Carnicom, and I'm here with Mark Kilcoyne today. And we're going to be having a discussion primarily on Mark's side about some of the recent research that has been done. This research is on the very forward edge of what I've been able to do, at least on the Morgellons issue. And Mark Kilcoyne has an extensive background. Both he has an active interest in the research as well as an extensive background in biochemistry and nutrition. And he's here today to give his thoughts and comments. He's aware of some of the research that's been done, and so I'm going to give the floor mostly to him. Mark, thanks a whole lot for being here today. I really appreciate it.
Thank you, Clifford.
And Mark, if you wanted, would you take just a second? I know you were at our conference last year in October of 2011, and the audience was very engaged with your talk very quickly. I know that. Could you give just a short background as how about this growth form over the past couple years? And I'll talk about my papers in more detail at another time, but you and I have had enough of a discussion where you're aware, at least, of the general basis of that work, and also the general chronology of that work over the past couple years. The first couple years ago being more general and basically a process of learning about disease in general and how we start to thwart disease in our body through the roles of antioxidation and enzymes and this type of thing. But that knowledge was actually a bit on the more general side, with the exception of very specific knowledge related to iron. Work on the existence of iron within this structure did come out in that earlier work. More recently, over the last few months, I have done work related to identification of specific amino acids, cysteine and a histidine, that we're going to talk about today, and then also some what you call mitigation or counter strategies involving reduction techniques of trying to break the bond